Let's say you're an abstract artist who puts circles inside lines. Not very well, but you know, you're just getting started out. You want to draw a circle fitting perfectly inside a perfect geometric curve. Oh, that seems to follow that. That sort of looks like the line y equals -1/2 x to the 4th plus x squared plus 1. This one. You want to find a circle that's going to fit right inside here and only touches at a single point, which we're going to call P. I just wrote an R. It's supposed to be P. We'll go with it. This kind of circle that touches only at one point here, those kinds of circles are called osculating circles. But how do you find where to put this osculating circle, what size to make it? How do you find that? Well, thanks to Leibniz's work on derivatives, you can find these answers with little trouble. Let's say that we want this circle to fit along the curve at the point 0, 1. So this will be along a plane that looks a little bit like this. The first step to drawing this circle is to find the tangent line at the point where we want the circle to touch the curve. So this tangent line will run right across here at y equals 1, and the slope here is 0. So that means that this radius will go across the line x equals 0. This is because the radius of any circle that touches a curve at one point, such as this one, will be perpendicular to the tangent line at that point, which we call P. So now we know that the radius will go along the line x equals 0, but we don't know how many units this radius needs to be. Well, this is where the calculus comes in. To find the length of the radius of the circle, you have to start out by finding the curvature of the curve and the circle itself, because at that point, the circle and the curve will have the same curvature. So the curvature formula is k equals the absolute value of y double prime over 1 plus y prime squared to the 2/3 power. I did that wrong, it should be 3/2. To the 3/2. That looks a mess. Okay. So y double prime and y prime will be the first and second derivatives of the equation that we already have. So we have that y equals -1/2 x to the 4th plus x squared plus 1. So we can find that y prime will be -2x cubed plus 2x, and y double prime will be -6x squared plus 2. So the next step is to plug these two formulas into the curvature formula. So we're going to get that k is the absolute value of -6x squared plus 2 over 1 plus, this is where it gets tricky, -2x cubed plus 2x squared to the 3/2 power. So then all we're going to do is plug in the coordinates that we had for our point P, which was 0, 1, and we're going to get that the curvature is equal to the absolute value of -6 times 0 squared plus 2 over 1 plus -2 times 0 cubed plus 2 times 0 squared to the 3/2 power, which will simplify to 2 over 1, which equals 2. So now we have that our curvature equals 2. This will help us find our radius because the radius of any osculating circle to a curve will be equal to 1 over the absolute value of k of t. So then we can easily see that this will become that the radius is equal to 1/2 units long. Back to our lovely drawing here. So we have that P is 0, 1, and our radius is going to be 1/2 units long. we know that the radius is going to be right here, and it's the center of this circle will be 0, 1.5. And we can go ahead and draw this circle. You can sort of see it there. And finally, we're going to write out the actual equation for this circle, which will be x squared plus y minus 1.5, because coordinate of the radius is, the y value is 1.5. Quantity squared equals 1/4, because the radius is 1/2